Right. Okay. So my iPad is visible, right?
Yes.
Good. Okay. So as last time, let's briefly recap what we did last time. So we discussed a generic Lorentz transformation, and then we argued that it's a group as an exercise to you. And then we looked at the identity part of the group. We then moved a bit away from the identity. And with that, we were able to derive that those transformations which live near the identity, they have to be antisymmetric. So this was the equation that they had to satisfy. And that also gave us accounting. If these are 4x4 matrices, then it turns out that we will have 6 such independent parameters. And 3 of them were boosts along each spatial directions, and 3 of them are rotations about those spatial axes. And then uh, we said that now we want to look at Poincare transformations, which are Lorentz that we looked at plus translations, right? And so we already saw that there are 6 of the Lorentz, and as you know, we are in 4 dimensions, so there will be 4 independent translations. So along x, y, z, and t. So t, x, y, z. So all in all, you will have 10 linearly independent transformations, which will be the whole group of Poincare transformations. Now, there was a question in the Slack, which I think I should discuss. Maybe I was a bit fast, and then we can proceed with the Poincare things. So there was a question as in why, some motivation behind uh, when I wrote this in terms of the Minkowski metric and the Kronecker delta. Why did it take the form? So let me argue that again. So you know that we have eta as a matrix, uh, which is the Minkowski matrix that remains, that is Lorentz invariant, right? So that satisfies this equation, which is the defining equation for Lorentz transformation. So what you can do is you can say that you want to express this M, because that's the only 4x4 Lorentz invariant matrix, as something like this. You see, mu rho nu sigma plus another function b, uh, mu sigma nu rho. Sorry. Yeah. Now, first of all, you see that you cannot have, so we know that rho and sigma are the indices that label the rows and columns of the matrix, and the antisymmetry is in these indices, right? Rho sigma is minus sigma rho schematically. So it means that on the right hand side here, you cannot have rho and sigma with eta. Okay, this is not possible because eta is a symmetric matrix, as you know, it's the metric tensor, the Minkowski metric tensor. So that rules this possibility. So then you can write a general ansatz in this way with A and B different. And now if you impose this condition, then you can immediately see that A equals minus B will follow from here. So that will fix M rho sigma to be just A and minus 1. And obviously there can be an overall scaling, but that's okay. Okay. Why there are 4 indices on this matrix? Yes, that's the whole point that I was trying to say. So you see, M rho sigma. So here to begin with, we are working in 4 dimensions, okay? And we are looking at position vectors x mu, t, x, y, z. And we are trying to look at linear transformations that act on x mu's. So by linear transformations, you know that these are matrices, these are linear maps. So that gives us 4 cross 4 matrix, okay? So in this notation, m rho sigma mu nu, this rho and sigma, they label the rows and columns of the matrices, okay? With rho being the row and sigma being the column. But these matrices also live in the physical space-time. So this mu nu are what labels the space-time indices. Okay, and recall where that came from. We said lambda is e power m because we want to look near identity. So when expanded, this was roughly this, right? Plus we neglected all second and higher order corrections. Now this, if you write down with indices, this became something like this, right? So these, as they stand, are space-time indices. But M itself is a matrix. In this case, 4 cross 4. And these are the row sigma indices. So there will be 4 indices. Okay. Okay. So this is how you can start with a general ansatz for the M's. And using the antisymmetry, you can antisymmetry in the row column indices, you can derive that A has to be minus B. But you can obviously have an overall factor. That doesn't matter. You can set it to 1. Okay. So that's why this is the form that I wrote. And there was a question in the Slack on this, so I thought of discussing this. There was another thing on the Slack, sorry, not on the Slack, but I thought maybe I didn't stress it enough. So note that, again, we will look at this equation. Okay. Now we argued that these m's, they satisfy something like a commutator equation written in terms of like schematically. I don't want to write the whole thing. And we said that this thing was what was called the Lorentz algebra or the Lie algebra of the Lorentz group. Okay. Now note that there was an exercise that these lambdas also form a group called the Lorentz group. Okay. But note these m's, they are not a part of this Lorentz group. That's something important to note, and I didn't stress it enough last time. So I wanted to mention it. And the reason is simply this, okay? Because you see, what was the defining properties or the essential properties of the M's? That was this thing, right? The antisymmetry. Now, as you know, that if something is a part of a group, then the identity lives there, right? And clearly the identity matrix doesn't satisfy this equation, right? An identity matrix is a symmetric matrix. It's not antisymmetric. Okay. So the question is, where do these guys live? And we precisely answered that question last time. So these M's are element of the Lorentz algebra, the Lie algebra, okay, which is a vector space. Okay. Vector space that was equipped with a commutator. So as we argued, so that's another important thing that I just wanted to mention, that these M's, they themselves are not a part of the Lorentz group because they're antisymmetric, and we know that identity is a symmetric matrix, so they can't form a group. But where they live in the Lie algebra of the Lorentz group. Okay, right. I hope that's clear. So with that, we can begin. Okay. So now going back to Poincare transformations. Okay. So Poincare transformations are again, we will denote it by lambda and a, where if you take a vector x, then the lambda is the Lorentz transformation, and then you do a translation on top of it. Okay. At times I will not give explicit indices on the equations, but it will be clear from the context. Okay. Like here there are indices, if you like, mu and then mu and then mu. But just for simplicity, I will be avoiding them most of the time. Uh, so this is how a Poincare transformation acts on a coordinate vector, like x prime. Now let's look at, and we already know how Lorentz transformation act on coordinate vectors. Now let's look at how these things acts on fields. Okay. So how these Poincare transformations, they act on field. Because at the end of the day, fields are the essential quantities that we are studying. Like we want to write down a Lagrangian, an action, and the dynamics of these things. So we need to understand what happens when these kinds of transformations act on fields. So as to preserve Lorentz invariance, or have to have a nice relativistic causal theories. So our first example will be scalar field. So a scalar field is just a function from R1, comma 3 to R. So from the space-time to any real number, and it will just be denoted by phi x. Okay, so there are no indices, extra indices on the scalar field. That's what the scalar means. And now let's consider just translations and see how it acts on a scalar field. So let's consider a frame which is just translated from the unprimed frame. And since this is a scalar, so by definition, we will have that phi prime in that new frame, x prime will just be equal to phi x. That's what the definition of a scalar field is. There are no extra indices. Now, this we can write as phi prime x minus a equals phi x. Using this equation, let's call it star 3. So by star 3, we get this. And now we can add and subtract a from both sides to get an equation like this. Okay. So that's what a translation does when it acts on a scalar field. And at this stage, we didn't demand anything about this vector with which we translated our whole coordinate system. But now let's look at infinitesimal translations. Uh, okay. And just as we argued in the Lorentz transformations case, that the important thing to look about the identity or infinitesimal transformations was that they were connected to the identity, and we already know that identity is like the part of the group. Okay, so again, following that motivation, we can look at infinitesimal translations just about identity. So now you can all Taylor expand the right hand side, and as you know from Taylor expansion, that this is what you will get. Okay. So this A is now a small parameter, infinitesimal parameter. And as usual, we neglect higher order terms. So this implies that the variation in the fields is this thing, right? And so that's what you get for a infinitesimal translation on the fields. And we will denote this as an operator acting on phi times a mu. And there's a reason why we called it P, because as we will see, this will be the uh, momentum operator. And for instance, you can recall from your quantum mechanics knowledge that this was precisely the momentum operator, right? And that's what we get here also. So that's the notation P. And for finite translations, we will again employ the procedure that we did for the uh, Lorentz transformation case. So what we will do is we'll exponentiate uh, this infinitesimal translations. Okay. So that's how we will get a finite translation. So where you now consider all order terms. For instance, here we neglected the second order pieces, but now here we will consider all order terms. And that's how you can form an infinitesimal translations. You can go to finite. This is true for any kind of group transformations, but continuous group transformations. Okay. Right. Now, yeah, so that's how this thing works. And there's one more thing I should say here, that note that when we considered action of translation on vectors, so the vectors work like this, right? And this you can imagine like a matrix, okay, like a matrix that captured this action of translation. But now we are looking at action of translation on fields. Okay. So fields which are like phi x. So that's why here the quantity that is analogous to the matrix is this p mu, that's del mu, and the action is like p mu phi equals del mu phi. So instead of matrices, now we have differential operators. Okay. And the reason is because now we are considering action on functions. So here in this case, this is a scalar function. So matrices, the analog of matrices now become differential operators. Okay. Right. And as we saw that from translation, we had this relation, right? For a translation of this kind. So you can check that for a general Lorentz transformation, this means the action on the scalars will be something like this. Okay. And a very easy way to see this is just consider translations. So if coordinates translated like this, the argument of this function it undergo the inverse translation. So that's why for fields, the action of Lorentz transformation changes the argument in this way. Okay. And this is how scalars behave under under a general Lorentz transformation, not just translations. Okay, now we understood the action of translations on fields. Now let's move on to the action of Lorentz transformations on fields. Okay, so again, our goal will be to find differential operators uh, that act on fields. Which generate these lambdas. Okay. So let's see how to do that. And again, it is exactly the same way that we did translations. So just to recap, we expanded it in a Taylor series way and then identified which is the differential operator here. So exactly the same thing we will do here, just with a few more indices, because generic Lorentz transformation has uh, one more index compared to translation. There's two indexes. Okay. So let's do that. Now, as you know that on vectors first, x prime mu for a Lorentz transformation looks like this. And we know that this is nothing but a finite version of this guy, right? As we argued last time. And because of the question that was asked in the chat today, sorry, it should be clear what these different indices are doing. Again, these row sigmas are for labeling the row and columns of M, and these are space-time indices. Okay. So it should be clear now what these different indices do. And if you now expand it out, then it becomes mu plus delta x mu, where it is x mu plus omega rho sigma m rho sigma mu nu x nu plus order omega square. Right? Now let's use this equation. So that's how the vectors work. So let's call this star 4. So from star 4, we know that phi prime of x goes like phi lambda inverse x. So that you can work out as the following. So that gives phi of x minus omega rho sigma m rho sigma mu nu x nu del mu phi plus higher order terms. Okay. And now recall that m rho sigma mu nu was written like this. Rho nu sigma mu. And this is exactly the same expression which I had written in terms of delta previously. So, but that included raising one of the indices. So if you raise one of the indices, you get deltas, okay? And that's because of this relation. Okay, so that relation, you can raise and lower indices and write it in this way. Okay, but now if you use this equation here in the first, like the leading, the subleading piece here, then what you get is something like this. So the piece we want to work out is exactly this. Okay. You see, this is the differential operator that will act on phi. Just like in the translation case, it was this that acted on it, right? So we want to isolate that operation here and try to find its expression. So this, now you can substitute this quantity, the expression for the m in terms of the etas. And if you do that, so let's do that carefully. X nu del mu. So if we do that, we get sigma mu x rho del mu rho mu x sigma del mu. Okay. So it's just this Kronecker hits this nu, and then you change the indices from nu to rho, like here. So that gives you a quantity like this. X rho del sigma minus x sigma del rho. Okay. And this equality comes from contracting the eta with this, so you raise an index. Okay. So we obtained a quantity, and we will call this L rho sigma, and we obtained quantity which does this now. Okay. Phi x plus omega rho sigma L rho sigma phi x. Okay. And yeah, so we can also write this guy as this to generate all the finite Lorentz transformations. Okay. So this is the action of Lorentz transformation on a field. And here the differential operator that we got was this. You can again write it all indices down as you prefer. Okay, so this is the differential operator that gives you like that generates a Lorentz transformation, a generic Lorentz transformation when acted on fields. Okay, scalar fields in this case, particularly scalar fields. Now there's a nice exercise that you can do. So you take L to be this and P to be this, and you can show that the following holds. Okay. So yes, so you can show that this thing holds. L mu nu L rho sigma is eta nu rho L mu sigma minus eta mu rho L nu sigma minus eta nu sigma L mu rho plus eta mu sigma L nu rho. So you can identify the first line as the Lorentz algebra, eta mu nu p rho minus eta mu rho p nu, and the last line is p mu is 0. Okay, so with this you can show that this holds, and this is what is called the Poincare algebra. Okay, just like we had the Lorentz algebra, this is the Lie algebra for the Poincare group. And let me briefly explain what each of these line means. So this we already know the first line, that's the Lorentz algebra, and that had to be there because every Lorentz transformation is by default a Poincare transformation, just without the translation. This tells you what happens to the generator that generates translations when you take its commutator with the Lorentz generator. And this also in a way you can use this as a definition of uh, the generator of translations from that property. So that's how a 4-vector transforms under Lorentz transformation. And the third thing is just says that translations commute. Okay, and that's why you get 0. But that's obvious because as we had argued when we started defining what a group is, we took the example of the translation group, and you know that translations, they do indeed commute, that translating by something and then again by something is the same as translating by the second thing first and the first thing first. So uh, this is like translations is a special kind of.
Yeah.
Sorry, was there a question?
Yes. No, I mean, yeah, it's obvious translations.
Okay, good. And that leads us to something that's called an abelian group. Okay, so an abelian group is a group which, in addition to the group axioms, also has this built into it. Okay, for all G1, G2 belonging to the group. So this is nothing but the commutative property. Okay, and translations do indeed do that. And this is the Lie algebra version of that. Okay, so that's what gives us the Lorentz, the Poincare algebra. Now, uh, a little bit of a difficult exercise, not difficult too much, but you just have to keep in mind more indices. So now let's consider vector fields. So a vector field will be this. Okay. So the vector index just translates normally using the Lorentz matrix, just it like it should, like a 4 vector. But this x prime translates in this way, or in other words, you can say that for a vector field, you will have something like this. Okay, if you just look at one point in x, then it behaves like this. So because of this, now you can again do Taylor expansion like we used to do, and identify the differential operator, and the differential operator that generates a Lorentz transformation on vector fields is this. So this is an exercise. So you can show that it turns out that it behaves like this. It has this as its expression. Okay. So this is an exercise for you to work out, that the L now modifies to this, where there is an extra piece now, and but in a way you can see that this had to be true, right? And the reason is uh, a vector field has an extra index mu, which is like a vector, like a 4 vector index. So that will have its own Lorentz transformation, but a Lorentz transformation that acts on the coordinate vectors, that kind of a Lorentz transformation. And what's that Lorentz transformation? We already know it's this M. And the remaining, this part comes from the transformation of x prime to x, just like in the scalar field case. So that's why you get this lambda piece that gives you M, and then this usual piece from the scalar field case that gives you this. So in some sense, this is again a trivial exercise, but I said a bit difficult because you have to take care of one extra index because it's now a vector field. But it's a nice exercise to do. Okay. So with that exercise being said, now let's formally discuss what are called representations. Okay. Because we now have built everything that we need to discuss representations and formally motivate them. So we saw groups, we saw their Lie algebras, and now we want to discuss what are called representations. So actually, in a way, we have already seen this, but let's now formally see what they are. And for this, recall that there are two things that we are always focusing. So one is coordinate vectors, which were the x mu's, and the other things was fields. For instance, for the scalar case, it was this. And now we considered action of these lambdas, this Lorentz transformation on x mu's and on the phi's. Okay. And as I explained, the first gave you these matrices M, mu, nu, and the second gave you these differential operators. So these are matrices, and we got differential operators like del mu, like L rho sigma, because they act on functions. Okay. However, you saw one important thing. You saw that these M's satisfied something let's call star, and the same thing was also satisfied by L, right? This L satisfied the exact same commutator that the M's did, the same commutator structure, right? So it means this was also a Lorentz algebra, because that's what we defined it to be. And this was also the same Lorentz algebra. Okay. But you see that on the left hand side, we have something that acts on coordinate vectors. On the right hand side, we have something that acts on functions. So in some sense, you see that this guy acts on vectors. So it's acts on a four-dimensional space, a four-dimensional vector space. But this guy acts on functions, which is infinite dimensional. Okay. Because recall what were the scalar functions? So they were functions of these kinds, right? So it's essentially an infinite dimensional space. So even though they're space where they used to act on a different, they still satisfy the same algebra, the same algebraic structure, the same symmetry structure. All these things are same. So this is what is the idea behind what is called a Lie algebra representation. Okay. So you can have different kinds of objects, just like M and L, and you can have them acting on different objects like coordinate vectors and functions, vector fields, whatever. At the end of the day, if they represent the same Lie algebra or the same vector space, which is equipped with a commutator structure, then they will be known as representations of the Lie algebra. So they are representing the algebraic or the symmetry structure in different ways because they are different objects, but underlying algebra is the same. Okay. So now formally, again, this is just a technical definition, but formally, uh, what exactly is a uh, Lie algebra representation is this, that you consider a group, okay? So a group G, and then you consider a map from the group G to something that's denoted like this. And let me unpack what this notation is. So this is a set of all linear maps T that map from V to V, okay? Where V is a vector space, just your usual vector space. So it could be a vector space of functions, which is infinite dimensional, a vector space of coordinates, which is finite dimensional, two-dimensional, three-dimensional, four-dimensional, whatever. And so you consider all linear maps on that. And rho, which maps from the space of group elements to this space that's a collection of all linear maps, that is called group representation. If this rho is also a group homomorphism. Okay, I'll explain what this is very briefly. So you know that, so let's understand what's homomorphism is. So you know that when you are studying linear algebra, you study vector spaces, okay? Then you study linear maps. But why do you study linear maps? Because linear maps preserve the vector space structure, right? For instance, a linear map from V to V has this property, right? Alpha V plus beta W is alpha times T of V plus beta times T of W. Okay. So linear maps are maps which preserve linearity or the structure of the linear algebra. Similarly, there are maps when you are studying groups, then you try to find maps which preserve the group structure. Okay. So what's the group structure? So if you have two group elements, then when you compose them this way, so when rho is a map from group G1 to G2, now this star is the group operation, okay? And this is the group operation in G2, which in this case, you can view it as composition of functions, okay, or maps. And this was group operation on G1. So you see, the meaning of preserving the group structure is this equality, that it nicely does the way group elements could be composed in this way. You can compose maps in this way. So maps which obey this are called homomorphism or group homomorphism. So in other words, linear maps will be called vector space homomorphism. Okay, so homomorphism is not such a difficult word. All it means, it preserves a group structure. Now let's come back to representation. So I said that a representation is something that maps from group to a space of linear maps. That's also a group homomorphism. So in other words, so we defined this. So in other words, for every group element, row of G, this is a linear map from V to B for all group elements. Okay. So you pick any group element, you will get a linear map from V to V. Okay. And this is because it's a group homomorphism. It preserves the group structure. Now, this is something nice. Why? You see, we like to study linear algebra, and it's also one of the first things in mathematics that you study formally because it gives you this structure of linearity. Okay. And linearity property is a nice property. Okay. Because that's the first approximation to anything. Now, when we abstractly defined groups like the closure axioms and the identity, the inverse, the associativity, they seem very abstract. However, now in this language of group representation, we are able to preserve the group structure and map it to a linear structure using this map row. Because now you have that for every group element, you have a map which is a linear map. So in this way, we can linearize the study of groups to the study of linear algebra. Okay, and that's what a representation does. And we actually, before defining all these things formally, we saw that this happens. How did we saw this? We said that lambda, which is a Lorentz transformation, was part of a group. Then we looked near the identity, and then we got something that had a vector space structure with vector addition and everything. So it had a linear structure. So that's why I said that from physics, we saw all of these properties emerging. Now we are just formalizing it. Okay. So that's what is called a group representation. Now, so this is a representation of a group G. Again, all of this could be a bit technical for you, but as I said, in this example of Poincare and Lorentz transformation from physics, we already saw all of this emerging. We're just formalizing them, okay? Now, for representation of a Lie algebra of this group, along with these properties of representation, it further has to satisfy the commutator structure, which is this, okay? That for any xy elements in the Lie algebra, for all xy belonging to the Lie algebra. That's again very natural because all we wanted to do by studying representations is to somewhere make connection to linear algebra. We already did that with group representation. Now on top of that, we have Lie algebras, which have a commutator equipped vector space. So this representation becomes a Lie algebra representation if it further satisfies or obeys this commutator, this preserves this commutator structure or the Lie algebra structure. And this is why precisely, explicitly we saw that there were two ways to represent the same Lie algebra, the Lorentz algebra, one with M's, one with L's. And the M's and L's are completely different objects. M was a matrix, L was a differential operator. One acted on four-dimensional vector spaces, one acted on functions. So they were completely different. Yet they preserved the Lie algebra structure, the commutator algebra structure of the Lie algebra. Okay. Yeah. So that's what I mean by representations of a Lie algebra and what formally a representation means. But because we discussed group representation, let's also see an example of a group representation. So here again, we will see first coordinate vectors and fields. So we already know that on coordinate vectors, this x prime acts like this, right? And so let's define a representation R which for every group element lambda gives you just the group element lambda. Okay, so this is like a very natural representation. So you take for every group element lambda in the Lorentz group, you just say that the representation is lambda itself. Now you can show that by definition the group homomorphism property is preserved, right? That if you multiply two matrices, this is nothing but just matrix multiplication, and we know that this is nice, okay, as a matrix multiplication. So this is already a representation. Now on the fields, let's define something like this, that phi prime, we know that phi prime was phi lambda inverse x, right? So we saw how the elements of the Lorentz group acted on scalars. So what does this mean? So we can define something like a representation U on functions as phi prime of x that just gives you phi lambda x. So what for every group element lambda, my representation acts on the space of functions or the space of fields, and in turn gives me this. Okay, so this U lambda. Now this is an exercise again given in the lecture notes. So you show that U lambda indeed forms a representation for the Lorentz group. Okay, not the Lorentz Lie algebra. And I want you to do this because then you will be clear that representations of groups and representations of Lie algebras are different things. And we also saw that groups and Lie algebras are different things. Like lambda formed a group, but this M and the relation was e to the power m, the exponential map. So that's also different things. So even though at times in physics we become a bit cavalier and forget about the precise distinctions between these things, but you should at least know at the back of your head that these are different things. Okay. So you can do this, try to do this exercise. And as I had said before, if you get stuck anywhere, as long as it's the exercise is not decided as a tutorial problem, which I haven't yet decided, I will be more than happy to guide you through it. Okay. Okay. One last thing again, that's and then we will begin with field theory. It's a bit of a notation. So, and this is a notation that's heavily used in physics. So we said that let's again go to the defining property of a representation. So you said representation was this row that takes group to a space consisting of linear maps from vector space to vector space. So here, as you saw, this M and L, they form a representation of the Lorentz algebra. Okay. And the objects like x mu and phi, which lived in this vector space, so v1 and v2, because they live in different vector spaces, so they transformed in the above representations. Okay, because they transformed uh, under the action of this M and L, right? So at times in physics, people again very like informally they say that these objects x and phi themselves form representations of your algebra. But what they are actually trying to say is these guys belong to vector spaces on which these representations work or act on. Okay, so that's why at times this might be confusing. So the correct thing to say is these coordinates and these functions actually live in the vector space here, and these M and L are representations. But sometimes people colloquially they say that the fields they transform, they themselves furnish a representation of things like this. Okay, so I just wanted to make that thing clear. Okay. Okay, so that's done now. So we understood how to operate or act Lorentz transformations on coordinates and on fields. So now we are ready to get to classical field theory, okay? Because now we understood how to construct causal theories. Yes, M is also called the generator. Yes, right. Because yeah, because it's like all the linearly independent elements of Lie algebra are its generators because they generate the symmetry group. And by generate, I mean this exactly this map. Okay, this map. So, instance, if you take an object in the Lie algebra, which is M, and then you exponentiate it, and you get the group. So, in this sense, it generates the group. Okay, so it generates the symmetry. The symmetry is captured by the group, so it generates the symmetry. So, all linearly independent elements of the Lie algebra are the Lie algebra generators. And yes, that reminds me of. Thanks for the question. That reminds me of something. I think somebody's mic is causing some disturbances. So I can hear some background noises. Yeah, I think that's fine now. Yeah, so there is a notion of a dimension of a representation, and that is nothing but the dimension of the vector space on which the representation act. So M is a four-dimensional representation, and L is an infinite dimensional representation because one acts on vectors, one acts on functions. Good. Now let's move on to classical field theory, and that is major content of today's lecture. So classical field theory. Okay.
Professor, can you just say that again? The X and mu is going to the vector space, but the representing they're not acting. But
Okay. Yeah. So there's nothing important about it. It's a terminology that at times physicists use very colloquially. So as I said, the actual representations are M and L. Okay. They are this representation rho, but they act on objects which live in this vector space V. So at times colloquially it is said that the elements of this vector space furnish a representation. So it's just a terminology that is used in physics at times. All I am saying is that the elements of vector space by themselves are not representations. They are just elements of vector space. They are the vector space on which the representation acts. So actually the representations are M and L, but colloquially at times we say that oh
X
the
and phi are representations, but they're not.
yeah, exactly. I mean, you understand what they want to say, but in the most strictest sense, they themselves are not representations. Yeah,
Right. Thank you.
no worries. Okay, so now let's go to classical field theory. So we know that we argued in the first lecture that we have to look at infinite degrees of freedom, and that gave rise to the notion of fields instead of just generalized coordinates and momenta as you used to do in classical mechanics. So we will be looking at fields, phi a of x, and this a at the moment is like a collective index. So this might just be a scalar field or a vector field, whatever. And so just like in classical mechanics, you had a Lagrangian. So now we will have what is called a Lagrangian density because it's like a per unit volume kind of an object. We will see this. So a Lagrangian density. So the good old Lagrangian of your classical mechanics can be defined in terms of this Lagrangian density in this way: phi of x and del mu of phi of x. Okay. So here there are two. So you see that because this is the volume, and so this is a per volume quantity, and hence the name density. Now, one important thing about this L that we will look at is, first of all, as we had argued, that we will be looking at the principle of locality very closely because it's a very important concept. So locality would mean that L can only be functions of phi x. It cannot involve functions like phi x1 and phi x2 at two separate points. Okay, this is forbidden by assuming locality. The second thing, it's more like a thing for simplicity, is what is called, we'll only look at Lagrangian involving only first order derivatives of phi. Okay. So that is, it can be a functions of del mu of phi x. So that's why I wrote that this phi and the first derivative of phi. So almost all the Lagrangians that you will see in this beginning part of the lecture and also later when you do QED and all that, they'll all only be involving first derivatives of phi. And this is actually something that can be relaxed and you can look at higher order derivatives. But there are some bad things that happen, and there are ways to deal with those bad things also, but I will not discuss. But I just wanted to, so for us, these two will be assumptions of all Lagrangians that we will write down. Okay. And but yeah, so don't dwell on this point more, that what happens if you have higher order derivatives and all that. Let's start the simplest case is only one derivative of phi.
Sir,
So yes,
can you explain the linearity property?
which linearity property?
For the Lagrangian density.
No, I said this is locality, not the linearity. You mean this?
Yes, sir.
Oh, sorry. Yeah, sorry for my handwriting. This is locality. This is not linearity. Uh, so by locality, I mean, let's look at an example. So can look at an example as a Lagrangian of this form. Okay. So you see that all of this implicitly assumes that they are all functions of x. Okay. You cannot, so this is what is a local Lagrangian is. What will be a non-local Lagrangian will be something like this. So you will have the first piece like this, evaluated at x. But you can have terms like this, plus m square phi square y, and x is not equal to y. So they are like well separated points. So this is x, this is y. So we are not going to consider these Lagrangians because these Lagrangians are non-local. They are functions of fields which are defined at different points. Okay, so that's all I meant, that we are going to look at Lagrangians where all these fields will be evaluated at the same space-time point x, not at x and y and z or whatever. Okay, so that's locality. Is that clear?
Yes, sir.
Good. Thanks for the question. Now the action, just like in classical mechanics, is just dtl, and that's dt d3x this l. And you can compactly write it as d4x times L. Now, here so that's the action, which is a straightforward generalization in the from the classical mechanics case. Okay, so now that we understand writing Lagrangians for classical fields, let's now move on to deriving equations of motions. Okay.
Euler-Lagrange.
Yes, Euler-Lagrange. Thank you. Very good. So the procedure is called Euler-Lagrange procedure. Okay, so we will exactly do the same what we did for single particle classical mechanics or many body classical mechanics, but there will be just more indices, and our main objects of interest are fields, not point particles. So we will consider a variation phi a. Again, this a is a collective index.
Can we take this to infinite dimensional? Those indices?
Yes, like if you're, as I said, like if you're, oh, you mean the space-time indices, the space-time indices. Sorry, did you mean the
Yes,
space?
yes.
No, the space-time indices, if you take them to infinite dimensional, that would mean that you're looking at a infinite dimensional space-time. I don't think that makes much of a sense, because you see, like our world is four-dimensional. Okay, so hence the physical space-time dimension is four-dimensional, and like if you follow string theory, then at max you say, okay, there are 26 dimensional, but again all of these are finite dimensional. So that's why the space taking the space-time index to infinite dimensional doesn't make much of a sense, and I don't think it gives you any important things.
It's not useful. Yeah.
Yeah, but what is useful, and thanks for the question, is the functions themselves live in an infinite dimensional space, as we argued. Like the coordinate vectors, they live in a four-dimensional space-time, but the functions themselves, they live in an infinite dimensional space. But the index still lives in the physical space-time, so that's finite dimension. There's a question in the chat.
I'm sorry, can you just explain that the functions live in the infinite dimensional space? What does that mean?
Oh, that means this, right? So what were the functions like in the scalar field case? So they were functions of this kind, right?
Yes.
Can you count how many independent functions are there of this kind?
How many types of functions are there of this kind?
How many independent functions are of this kind? Is that a finite number?
That's an infinite number.
That's what it means, that this is an infinite dimensional space. Okay.
All right, I will take up more time.
No, all it means is the space of functions that satisfy this thing belongs to a space which has infinite number of independent functions, right? For instance,
Okay. I got it.
right. For instance,
Yeah, I got it.
yeah. One concrete example would be recall Fourier series. So in Fourier series, you would know that any periodic function phi could be expressed as sine mx and cos nx, right? But this m and n, they went till infinity, right? Right?
Yeah.
So you see this vector space which is spanned by sine mx and cos nx is infinite dimensional. So periodic functions are one such example. Periodic functions again live in an infinite dimensional space.
Okay. All right.
So all I meant is this. Yeah, maybe I used a heavy technical jargon, but all I mean is this, that in Fourier space, you know that, yeah. Okay, there are some questions in the chat. Let me address them very quickly, and then I'll continue the Euler-Lagrange. So there's a question from Adil that feels weird that two homomorphic representations have different dimensions. Yes, so that's fine. Okay, why? You see, homomorphism. So this has got to do with the word homomorphism. So I said homomorphism are maps that preserve some structure, whether it is the group-like structure or the linear algebra structure, they just preserve that much. I did not say that they are bijective. Okay. I did not say that this map is one-to-one and also onto. Only when you can say that they are bijective, you will have what is called an isomorphism, not an homomorphism. So that's an added property on top of homomorphism property. And then you can expect that there are, if two representations are isomorphic, then the underlying vector space dimension should be the same. But here I didn't claim that M and L are isomorphic. I said that they are separate homomorphisms. Okay. So I think this is what you had in mind when you said it's weird. I'm just trying to guess that was your question. Okay. Why the Lagrangian density only the function of fuzzy? Yes, as I said, we will not dwell on that. I said that I just took an extra additional assumption just to simplify things, and all the Lagrangians that you will meet will be this. Okay, where you will only have first order derivatives, and I won't explain much on this because it will be beyond the scope of this lectures. But I can only tell you this, that when we will do Euler-Lagrange, given that you have in the argument of the Lagrangian density first order derivatives of fields, Euler-Lagrange will give you second order derivative of fields. So the equation of motion will be second order in the fields. Just like in Newton's laws, we had second order equations of motion. Now there is something special about second order equations of motion. If you take higher order derivatives in the field, like second order or some or higher, then you will get third order or fourth order equations of motions. There many weird things happen, like you will get states which will have negative norms. These are called ghosts. Okay, and those are not nice things. Again, we will not discuss this, but if you want, that's just a one line reason. Okay, so now let's do variation. So for a general variation, phi to phi plus del phi, so we can write down the variation of the Lagrangian like this. Okay, this is just chain rule and total derivative, the concept of total derivative. And now we can write down the same line a little bit differently. Okay, so here what I did is I exchanged the variation of the fields and the space-time differentiation. And that's fine to do because we are considering arbitrary variations. So this is like a arbitrary general variation, and this was just like a space-time differential, so we can change them on top of each other, because you see this arbitrary variation is a variation of the fields, not the variation of the space-time points, and but this acts on space-time points, so that's why I'm allowed to do this. And now you can do integration by parts. On the second piece, over here. So if you do that, you get a total derivative piece. So this is again just product rule, and a piece that acts on the Lagrangian only, but not on the variations. Okay. Okay. Now, just like in classical mechanics, and this is something which we will do all the time, this is a total derivative term. So just evaluating that piece is something like this. And that, as you know, you can use what's called the Stokes theorem to write it as some quantity. Actually, let me do like ds times this quantity, whatever that was inside, okay, as a vector. And this is just the Stokes theorem. And now we will further assume that fields die at infinity. So fields go to 0 at infinity, and hence you can drop this term. So what you are left with is just this piece, d for x, the variation, minus del mu, del L, del, del mu phi a. Okay, so that's what we get. Now, since delta phi a are arbitrary and independent, so each variations was arbitrary and independent. So if the action is 0, then that implies that this integrand must itself vanish. Okay, and this is again just the field theoretic version of the Euler-Lagrange equation which you studied in classical mechanics. Just there are more indices, infinite dimensional space where the functions lives, and that's it. So this is what is called the Euler-Lagrange equation. So demanding that field configurations which extremize the action, which means this, your action is a stationary object under these kind of field variations. So those field variations need to satisfy this equation, which is called the Euler-Lagrange equation, and that gives you the equation of motion, understanding which we will reveal the dynamics of your system that you are interested in. Okay. Now, yes, another thing is so this is again a notation, a very heavily used notation in QFT. So all field configurations which, so let's note this as star 5, which satisfy star 5 will be called on shell. Okay. So every kind of equation or expressions that we derive, or every field configurations that we study, if that comes from the equation of motion, if that uses the equation of motion, which is star 5, then we will call all of those expressions, those identities, as on shell expressions, identities, or on shell field configurations. Okay. And towards the end of today's lecture, we will see certain expressions which are off shell, which are just identity by themselves. Okay. So yeah, so they don't require equations of motion. So they will be off shell quantities or off shell expressions or off shell field configurations and so on. So again, that was quite straightforward from classical mechanics, just generalized. Now let's look at some examples. Okay, now let's look at some examples of some Lagrangians. So one example would be the Lagrangian of a real scalar field. Okay, so that is given by this quantity. We already saw it actually when we were discussing locality minus some potential phi. Okay, so that's a so phi is a real scalar field. Real, so scalar you already know, and real means it's a function from the space time to real numbers. Later we will see complex scalar fields, which will be a function from space time to the complex numbers. Okay, so that's what real and this thing means. And if you expand it out using the Minkowski metric, so you can write down the time component as this and the space component as a gradient of a scalar field, and gradient square, and the potential piece. Okay, so that's what it looks like when you write it in terms of the specific components, the time and the space components separated out. And so now if you want to connect it to usual classical physics, so this can be seen as a kinetic piece. So this is like a kinetic term because it involves the time derivative. So this is in some sense like a p square over 2m term. And this whole thing is, if you like, the potential energy. Okay. But this is again just analogy because since we are dealing with classical fields, there are no direct relations. So these are just analogies to help you explain, understand. Right. Now, there could be any choice of this V phi that you can take, but it has to obey again locality, and it has to be like a smooth function so that you can differentiate it and everything. So one such example of V phi is, the simplest one is just half m square phi square. So this is again nicely local. This is infinitely differentiable. So all of that properties are there. So this is a nice and very simple Lagrangian. How can we find this kind of Lagrangian? Okay, there are some more questions. So could it be a reason that if the Euler Lagrange becomes fourth order, then there might be some reason? Can you explain the second line one more time? Oh, the second line. You mean the line here, right? Yeah, so by the second line, I meant that you see here we can exchange the variations and the derivative acting on the space-time coordinates because they are kind of independent, right? These are arbitrary variations of the field themselves, not acting on space-time points, but fields. Like phi going to delta phi or phi going to phi prime, these kind of variations. So you can change them without any problem. They are not involving space-time dependence. And del mu is the derivative operator acting on space-time dependent objects. That's why I said we can interchange them. Could you please solve a problem here? Derive the conserved charges from the... Yes, I will solve that problem of deriving conserved charges from Lagrangian only when we go to what do we mean by conserved charges. We have not yet understood what they are, not in this lecture. How can we find these kind of Lagrangian expression? Okay, so we are looking at some examples of Lagrangian. So given for an arbitrary system, it's a very hard problem to determine its Lagrangian. Okay, and we unfortunately we won't be doing that in this course because, as I said, it's a very hard problem. Like given an arbitrary system, we cannot write down the Lagrangian just by itself. At times, some symmetries help us to predict what the Lagrangian will be, and then there are many interesting things there. Okay, so I will probably answer this question at the end of the lecture. Then there is a question on shell. Yeah, on shell again. This is just a terminology, but I had to introduce it because it's used in physics textbooks very much. So as I said, on shell, we will see this also again throughout this lecture today. So on shell means any expressions, any field configurations which uses the equation of motion, this equation or the stationarity of action. Those things are called on shell. We will see an example like in 15 minutes, and then we will contrast it to another example which will be off shell. Okay, then that will be clear. But all
Do
that
you want to talk about massive and massless here on shell and off shell? You want to talk about that or no?
No. I won't be talking about that. That will,
Okay.
yeah. That probably we won't see because that notion of on shell and off shell comes when you do interaction or interacting theories. Okay, we won't be doing that now. But other lecturers who will be teaching you interactions, we will do that. Yeah. Okay. Let me carry on. So yes. So now if you do this, so then as an exercise, you can write down the Euler-Lagrange equation for this system where the Lagrangian is given like this. Okay. And actually, let's not do this as an exercise. Let me do this here to show it to you how it works. So what was the Euler-Lagrange equation? So in this case, this reduces to this because we just have one scalar field. So we can drop the A index altogether. Now, let us first compute the del L by del phi term. And that in this case is just minus half m square and the half goes away. So this, okay, minus m square phi. So that is the differentiation of this piece. So that gives you that, okay. Now let's compute del L by del mu phi. And that is precisely this piece. So to compute that, what you can do, so you can take the half out and you can expand the Lagrangian using the metric a bit. So you can write this as eta mu nu del mu phi del nu phi. Okay. So you can do that. Now, eta is a constant matrix, so you take it out, and yes, this is also another thing which you should keep in mind, and you should not do as I am doing now. So this is a mistake. So you should always, when you are differentiating, you should always take different indices in your Euler-Lagrange equation from the one that is given in the Lagrangian. So for instance, you take these as alphas and not mu's, okay? Otherwise, you will end up committing errors. And the reason is this index alpha is a dummy index, it's summed here. Similarly, this index mu is a dummy index summed inside the Lagrangian. So there is a priori no reason they should be equal, okay? So this alpha is different from these indices. So don't do the mistake that I was doing, take them different. Now, if you do this, so if this alpha hits the mu, again, just product rule. So that gives you a Kronecker delta like this. And if it hits the second piece, then it gives the Kronecker delta like this. Okay. And the reason is this identity. This is delta alpha mu. Okay. And it should be clear why this is the case, because only when alpha equals mu, you should get this quantity star to be 1. And if alpha is not equal to mu, then star should just give you 0. And hence, that's also the property of the Kronecker delta. So you get delta alpha mu. And the way these indices are placed is this is placed below. So if mu in the numerator is below, so that's the lower index. In the denominator, if you have a lower object, then that is placed in the upper index, just to be consistent with the index notation. So with that, you can quickly write down this thing as eta mu nu over 2. So let's take the eta inside. So you get del alpha nu alpha phi, and then similarly from the other also you get del alpha phi, and you get just this. Okay. Now what are the Euler-Lagrange equations? So you have to take a del alpha of this quantity. So that means del alpha phi, and then you have to subtract this piece. Okay. So if you do that, you end up with del alpha phi plus m square phi equals 0. Okay. So we got our first equation of motion, and this is called the Klein-Gordon equation. We will see maybe in 2-3 lectures from now what this means. But at the moment, this is just an equation of a real scalar field. But we will see what physics it describes later. So it actually describes the physics of some simple harmonic oscillators. Okay, but we will see that later. For now, this is just the equation of motion that we used, that we derived using Euler-Lagrange equation for a real scalar field. Right. Now, there are some exercises in the lecture notes which I encourage you to try, which will also help you to generalize. So here we did this for a scalar field. So you can generalize this to vector field, tensor fields, whatever you want. So this exercise will generalize it to a vector field. So we will consider the Lagrangian like this, defined like this, plus half del mu a mu square. Okay. So whenever you see a square, it's better to, another trick, it's better to write down in terms of the metric. Okay. So that you get all the indices correct. So you can expand this out in a square, expand the square out. And then the exercise is that what are the equation of motions for this vector field a mu. Okay, so use the Euler-Lagrange equation and do that. And also I have added in some more notions in that exercise, and you are encouraged to do that. And if you do that, you might learn something. And again, if you get stuck, do let me know. Okay, there is a question in the chat. What's the difference between all? No. So Noor is asking a question. What's the difference between Euler-Lagrange equation and Klein-Gordon? So Euler-Lagrange equation is a general prescription to derive equation of motions for any arbitrary fields, arbitrary theories, arbitrary Lagrangians. But Klein-Gordon equation is the theory which is described by a Lagrangian which has this form. This form. So it is the Lagrangian of a real massive scalar field. And the equation of motion that you get from it is called the Klein-Gordon equation. So there are not two different notions. It's that Euler-Lagrange is like generally for any Lagrangian, and Klein-Gordon is the one that works for, that's the equation of motion for this particular Lagrangian. Okay. So in that sense, a Klein-Gordon equation is also an Euler-Lagrange equation because it is the equation of motion of one particular theory, one particular Lagrangian. Okay. Yes, mu equals 0 is indeed the time derivative. And sorry that if that was not clear, but recall that I was writing coordinate vectors like this. So my notation of coordinate vectors was this. So hence the 0 component was time and all of these are space components. Okay, thanks for the questions. Okay, cool. So we understood a simple example how to do all these variations. Now let's move on to the next important and probably one of the most important concepts in classical field theory, what is called Noether's theorem. And this is where I will discuss the conserved charges thing that was pointed out in the chat. Okay, so Noether's theorem. So maybe some of you have already seen this in the classical mechanics course. So let me recall people who have already seen it and what does this say, and then we will explicitly see how it works. So now in classical mechanics, what Noether theorem tells us, and this is why it's a very powerful theorem, that if you have translational invariance in your system, for instance, if you translate your system and the physics remains the same, the observables that you compute are the same, then it hints to a fact that linear momentum is conserved in your system. If there is rotational invariance in your system, then it means that you will have conservation of angular momentum. Okay. And the third thing is if there is time translational invariance, not just space invariance along the space, the time translational invariance, then energy is conserved in your system. Okay. And these are very powerful things because just from observing what symmetry my system is satisfying, I'm able to get conservation laws from them, powerful conservation laws. And so we will derive what I said just now, and then it will be clear that these are the implications of such symmetries. But one quick thing to note is, and many of you would have already noticed, that you see, I said space translations, momentum conservation, rotations, angular momentum, time translations, energy. So you see, it's true that we haven't yet seen how this works in field theory, but you can already see why they are paired this way, why space and momentum, rotations and angular momentum, and time and energy are paired. And one of the easy way to see this, like as you know, even in classical mechanics and also quantum mechanics, that the pairing is between the object and its conjugate momenta. Like position, the conjugate momenta is linear momentum. Then any angle theta, which deals with rotations, the conjugate momenta is the angular momenta thing. And then for time, you have energy. And from quantum mechanics, you also know that just like there is a uncertainty for momenta and position, there's also uncertainty for time and energy. Okay, and again because these are conjugate to each other quantities. Okay. Okay, so with that in mind, so at least we understand the pairing, why this pairing has been done. Now let's see why such symmetries lead to such conservation. So we will start with an example, and this will be the example of a complex scalar field. So now we will have two fields, phi, phi star, and their derivatives. Okay. And the Lagrangian is going to be del mu phi star del mu phi minus m square phi star phi. There's a question. Time as an operator. Okay, we will discuss that later. That's not relevant to what we are doing now. Okay, so this is the Lagrangian, and uh, because phi is complex, so phi maps, as I had said earlier, from space-time to complex numbers. And the way this Lagrangian was written this way is to ensure that L is real. Okay, so that's another physical assumption that we will be taking, that the Lagrangian densities will be real. So that directly enforces that whatever parameters like m and other things that you will be writing will also be real. Okay, and that's important, right? Because m, let's say, is like the mass of the field, as we will see. The connection with the Lagrangian should be. Okay, so I won't discuss that now. Okay, sorry. Let me move forward. So now you see that let's talk about what are the symmetries of this action. So you see that if you take phi and you transform it to e to the power I alpha phi, where alpha is real, and you do the opposite for its conjugate, then the action and actually in this case L is invariant. So it remains the same. Okay, and the reason is very simple, because you have each term here is like a conjugate pair. So you have phi star, phi complex conjugate, and here again complex conjugate. And just a notation, this ei alpha for alpha in reals. So this what is meant as the U1 group. Okay, so this is known as the group of uh, unitary 1x1 matrices, or just numbers, and by definition they have to be e to the power I alpha or just a phase. So this is what is said, that L and the action here, both the things are U1 invariant in this case. Okay, and you see I stressed this thing, that the action and the Lagrangian are invariant, because what can happen is, you see the action was actually the integrated version of the Lagrangian. Okay, so this was the Lagrangian, and that was the action. Now you can always add some total derivative terms to this action, like del mu k mu. Okay, so you can add some extra piece, and the delta s equals to 0 will give you the same Euler-Lagrange equations. So let me put a coefficient here for the case alpha non-zero and the case alpha equals 0. Okay, and the reason is, as we had argued before, we will drop these boundary terms. So like we did here by this argument, that we will drop total derivative terms like this, because you can write them as a surface term, a term at infinity, and then you will say that there is an assumption that my fields, they die at infinity, so you can neglect those terms. So hence it's a very trivial exercise. You can show that any like this piece will also preserve the action. So whenever the Lagrangian uh, transforms as a total derivative under your symmetry, the action remains invariant. Sorry. Yeah, S is invariant under that action. But in this particular case, the action and L both are invariant. Okay, so that's why I specifically mentioned that both of these things are invariant in this case. Okay, Now, for this symmetry U1, there are some important things to note. First of all, this is a continuous symmetry. So by continuous symmetry, I mean this alpha belonging to real number was a continuous parameter. Furthermore, the way I wrote this is a global symmetry. Okay. So global symmetry meaning that alpha was a constant. So it acted the same way at any space-time point. It was not dependent on space-time point. To contrast, a local symmetry will be the one that is dependent on space-time point in this way. Okay. But you will see later in the course that such symmetries can also they also have a different name called gauge symmetries, but we will not discuss this here at all. Okay. So, and again, as before, we can do we can play the infinitesimal version. So the infinitesimal version would be just to expand. So we know phi goes to phi prime, that was ei alpha phi. Now you expand this as 1 plus I alpha phi. And similarly, you can find what's for the phi prime. So, the reason that we could do this was because alpha was a continuous variable. Okay, so we could do this. Now, to contrast the first point of continuous symmetry, let's look at an example of a discrete symmetry. Okay. So there is a discrete symmetry that I have written in the typed lecture note, but I decided to do another one here so that you can read from the notes. But a different one is this. So consider again the Lagrangian for the real scalar field, not the complex. Sorry, no square, minus half m square phi square. So now consider a transformation that takes phi to minus phi. Okay, if you do that, then L is invariant under this. And because L is invariant, that means S is also invariant. So this is indeed a symmetry. Now, the group for this symmetry is what is called a Z2 group. Let's not go into the terminology much, but it's a group made up of two elements, 1 and -1. And the group operation is just multiplication. Okay. So it has just two elements, 1 and -1, and the operation is group multiplication. Okay. So that's why the inverse of -1 is just -1, because -1 times -1 is 1. So it is a self-inverse thing. And why this is called Z2? Let me just quickly say. So now all of us know how to read a clock, right? So what happens in a clock? So this is a clock for telling the time. So we say that in a clock, a 13 is same as 1, 14 is same as 2, right? So why do we say that? So what we have in mind is when you take 13 and you divide by 12, you get 1. When you take 1 and you divide by 12, you also get 1. So this identity essentially says that the remainders are the same. So the right way to say this is 13 is equivalent to 1 mod 12. Okay, the mod operation does this. So the Z2 that we talked is essentially a clock with two entries, -1 and 1. And quantities which are mod 2 are same. So that's why 3 will be same as 1, 4, and so on. Yeah. So that's the notation for the reason why we said Z2. Okay. So you can in fact, yeah, I think that's fine. So so that's the idea behind the Z2. And note that this was a discrete transformation, right? So it took a phi and just flipped its sign to -phi. There is not a continuous way to do this. Okay. And we saw that directly from the group also. Like the group of U1 was ei alpha, where alpha was a continuous parameter. But here there are just two discrete objects. They don't talk to each other. They're very discrete, but it's still a group. And because of this, you cannot now write an infinitesimal version of this, because the way we could write this infinitesimal version was because the parameter was continuous. We could Taylor expand, and Taylor expansions involves taking derivatives and these kind of things. But taking derivatives means the function should at least be continuous. But here it's not the case. So you just have a symmetry, but there is no analogous infinitesimal version of this. And we have already seen this in the Lorentz transformation case, where we had the P transformation, the T transformation, and all that. Okay. Okay, so that's an example of some symmetries of Lagrangian, continuous and also discrete. Now let's state Noether's theorem. So Noether's theorem states every continuous symmetry of the action gives rise to a conserved current. Okay. So in this, we already understand what continuous symmetry of the action means. What we need to understand is what is this word conserved current, that we will see now.
Is it also the other way around? Conserved current means there is a continuous symmetry.
That is a very good question. Very, very good question. And we will end today's lecture by seeing that that's not the case. Okay.
Okay.
Yeah, but it's a very subtle point. It's a very good question also. Okay. Now let's look at the proof of it. So let us consider phi A plus some parameter, a small parameter times delta of phi A. Okay. So this is some transformation, and we want to consider that the action is invariant under this transformation. So we want to argue that S of phi A plus epsilon delta phi A, that is S of phi A prime, minus S of phi A, which you can denote as this. This is 0. If this is true, then this transformation will be called a symmetry by definition. Okay. Okay. Now, to prove the theorem, we will use a trick. But let me write this in red, because I have to emphasize that this is just a trick. It has no bearing on my theorem or anything. Okay. So this is just a trick. So the trick is, so this parameter that we consider epsilon, let us promote it to a space-time dependent parameter. Okay. So with that, our variation of the field becomes like this. Okay. So now, because of this, you see, this variation of the action because of the transformations, that has to be proportional to the derivative of this parameter epsilon x. Okay. Because that means that if epsilon becomes constant, then we will get a symmetry, that is del epsilon s is 0. Hence, at leading orders, the variation in the action should be proportional to the derivative of the epsilon, okay, which we have now promoted to a space-time dependent object. So by promoting it to a space-time dependent object, we have broken the symmetry that we began with, this symmetry. Okay. So that's why the variation of the action should be proportional to the amount which is it breaks, which is the first derivative of it. So if that's the case, then you can write down this object as del mu epsilon, but since it's proportional to it, so a proportionality factor j mu. Okay, some proportionality factor. Now, what you can do, our best friend, that is integration by parts and throwing away boundary terms. So if you do that, you end up with this thing plus a total derivative piece, okay, which we can neglect. So we can neglect this. So that means that delta epsilon s is 0 if and only if del mu j mu is 0. Why it is that? Since these epsilons that we take are arbitrary functions. Okay, they are just arbitrary and independent functions. So this is the same argument that we used in the Euler-Lagrange case, that if some arbitrary and independent functions are multiplying an integrand, so if the total integral is 0, then the integrand must vanish. Okay, this is like one of the main theorems of calculus of variations, if you want to be rigorous. Okay, so that means we proved that an equation like this holds, that J mu is a conserved current. So J mu, so if that equation holds, then J mu is known as a conserved current for the symmetry transformation pi a going to phi a plus epsilon delta phi a. Notice now we can take this to be constant again, because we just used it as a trick, and that's what I wanted to highlight. That remember, this is just a trick. The trick was to do that and using the fundamental theorem of calculus of variations, argue that this equation holds. That's it. It has no bearing on any other thing. And because some of you might not be satisfied that this is just a trick, we will also prove Noether's theorem in a different way. But for now, this works. Now let's look at some examples, okay? Actually, before that, let's discuss the notion of conserved charge. So, and this is something we already discussed a bit in the first lecture when we discussed continuity equation. So this equation implies that you can now write down it in terms of its components, time and space separate, in this way. And now what you can do is consider the integrated version of this. So we will do d3x jt plus d3x del I ji equals to 0. Okay. And now again, this is like over the spatial coordinates x, y, z. This is a total derivative. So by Stokes' theorem and the way we discard derivative terms, we can get rid of this to 0. And what we are left with is this quantity is 0. And you can define Q as this object. And we have shown that del T of Q is 0. So Q is a conserved charge. And the notion of conserved charge should be clear, because in classical electrodynamics, as you very well know, there is a continuity equation like this. And there the charge density, the electric charge density, is exactly this Q. You denote it by rho, right? So yeah, so that's why this is a sorry, not this. Rho is this, and when you integrate it over volume, you get the conserved charge. And what this equation says is, if you measure the charge at this point of time, and you wait for some, let's say 10 seconds, 15 seconds, or a year. If that's the only symmetry of your theory and there are no other things disturbing your theory, then the quantity will still be the same, this quantity Q. So it's independent of time. That's what conservation here means. And when we quantize this theory, we will have something more to say in terms of the quantum theory. Okay. Right. So now let's compute for the complex scalar field what conserved charges we have. So there the symmetry was this, right? Okay, so it's already 4, but because I started late, like 10-15 minutes, I hope it's fine if I go till 4:15.
Please continue.
Okay, good.
Thank you.
Yes. So for the complex scalar field, now you know that del phi is just I alpha phi. So the way to look at it again, look at the infinitesimal version. So whenever you get stuck in field theory, you look at the infinitesimal versions, and that will give you an idea where to go. And because it's a continuous symmetry, so you can do that. So del phi is this, and del phi star is this. So I'll be a bit quick here because this is very straightforward. Now we take alpha to depend on space and time. And now if you compute the variation of the action, then it will give you something like this. So again, this is very straightforward. And because we discussed the transformation very carefully, I'm being a bit fast here. But this is just taking derivatives and nothing more. The only important piece that I will give you here is, so you see in this infinitesimal version, we omitted alpha square piece, okay? So we neglect anything that's second order and beyond. Similarly, when you are doing this variation, you omit all order alpha square and above pieces, okay? That's probably only one important thing that I have to say to derive this result. Rest, everything is straightforward. So now if you do this, you substitute here in this deltas, these equations. So this goes here and this goes here. And if you do that, you end up with something like this. Del mu alpha, I del mu phi star phi minus I phi star del mu phi. Okay. Now, as we argued, anything that's proportional to del mu alpha is the current. So this is the current. So that's why the current reads phi star phi minus phi star del mu phi. And because del S is 0, that implies that this guy is conserved. Okay. Now, from quantum mechanics, you know that this is pertaining to an exercise which I had given in the first lecture, that there is also a continuity, local continuity equation there. And the exercise was, what does that continuity equation correspond to? And that corresponds to what is called the probability density and the probability current. And as we know, the probability is a concept that is conserved in Schrodinger equation or in quantum mechanics. So from that, you could see that this guy has a similar feature, okay? Because recall that in quantum mechanics, it was written something like this, right? And uh, so this has the same schematic form but now with completely covariant notations with all space-time indices properly. So that's why you can see that the result that we get, that there is a continuity equation for that symmetry of U1, is indeed a correct equation, and you can consider it as an analog of the probability conservation equation in quantum mechanics, but now completely relativistic. Okay, so we will so this quantity is conserved, and yeah, and we can construct the charge from it, which is just the three-dimensional volume integration of this Jt, and that gives us this quantity. Okay, phi star phi minus phi star del t phi. Okay, and later when we will quantize the theory, we will see that this will actually commute with the Hamiltonian, which, as you know, in the Heisenberg's picture is saying that this thing is zero, right? So all of this will fit in nicely when we quantize the theory, but at the moment we have only seen the classical version, which is that we have a conserved current. Okay, now for the remaining part of this lecture, we will discuss another example, and we will stop there. Okay, so that example is what happens when we consider space-time translations. Okay, so say that you have a theory, you have an action which is invariant under space-time translations. Then what are the conserved currents that you get out of it? For simplicity, for simplifying notations, I will introduce a quantity which I will call pi, which will be just this thing. Okay. Now, for space-time translations, we know that this is what it means. So we are translating by a parameter epsilon, and we did this very slowly and rigorously, so I can be fast now. And again, neglect second order terms and higher. Okay. So this implies that delta phi a x is minus epsilon nu del nu phi a. Okay. So now we will promote epsilon to a function depending on the space-time coordinates, and we will do the variation. Okay. So delta s is plus phi mu of a delta del mu phi a. Okay, and now note that this delta del mu of phi a part will play a key role here. So we already argued this step. We said that we can exchange variations and space-time derivatives. But now, because delta phi a is this thing, so this del mu will act on both the things, and what you will get is minus del mu epsilon nu del nu phi a minus epsilon nu del mu del nu phi a. Okay, so if you take this and put this here, then you can write delta s as minus. I would urge you to carefully go over these derivations again. That will give you practice, and also to check that I have not committed any mistakes, like a minus sign or a index up and down, and you can point it out to me in the class next.
Right.
So you get something like this. Okay, this is again a very simple thing that I just substituted this there, and that gives me delta S as this. Now note that we can write the variation of the Lagrangian as just this, right? So that is just this. Now from here, we can write down that if we vary the Lagrangian with respect to a space-time derivative, then it just becomes this. Where this pi is this quantity. Okay, this is pi. Del mu phi a. Okay. So I used the variation of the Lagrangian to write down the variation of the Lagrangian with respect to a space-time derivative as this. And this is again just writing total derivatives out. Okay. Now we see one important thing by doing this is we see that there is this quantity already hidden here. Okay, you see that we have this piece as this piece and this piece as this piece times an epsilon. So you can club them together now in a nice way. So delta S. So what I'm trying to do is express the variation of the action as the variation of the Lagrangian density plus some terms. So by doing this, we got to this point. So the piece which depends on the variation parameter epsilon and the piece which doesn't have any derivatives of it. Okay. So you have the derivative part on the epsilon and non-derivative part. So now we can do again our favorite integration by parts and throw away all terms to write all total derivative terms to write this as this quantity epsilon nu okay, and this object, and as before we will say that anything that is proportional to the derivative of the symmetry parameter will be called a current. So we will say this current as a quantity called T mu nu. Okay. And because delta S is 0, that implies that we will have this conservation. Okay. And so I think we have to stop for today, but we will explain what this quantity means. But let me just mention that this is what is called the stress energy tensor. So this is called the stress energy tensor. And we will see that when we look at the conserved charges, which in this case will be, as you very well know, the time component, so T of nu. But now this charge will have an extra index nu. So we will see that we can call this P nu. Sorry, we will call this P nu, yes. And P0 will give us energy, and Pi will give us linear momentum. And so these parts we will see how to do this, and like we will do this in an example. Actually, if you want, you can directly give a try. So the exercise is this, but this has been worked out in the lecture notes, so you can directly look at there. So you just take the scalar field that we discussed, and then compute these quantities P news, P0 and Pi from it. And then you will see that you get something that looks like P0 as energy and Pi as momentum. And again, this was expected because we started with demanding that our action will be invariant under translations. But note that here by translations, we mean all translations. We said space-time translations. So there are space translations and time translation. And space translations correspond to momentum and time translations correspond to energy, as we had argued. So Noether's theorem tells us that. Okay. So I think that's a good place to stop. And we will then look at, yeah. So there are two more pages to go to conclude classical field theory, and then we'll start quantization. Okay, maybe last few minutes were a bit fast, but as I said, these are all simple steps because I told you the critical parts of the steps what you need. With that, you should be able to reproduce all of this. But is there any question?
When do you expect to give us assignments?
Sorry?
When do you expect to give us assignments?
Yes, that's a good question. That's what I was discussing with Mishal at the beginning. And it turns out that probably by the end of this week, we should be giving you assignments, I think, though I'm not totally sure. But I think Mishal can chime in maybe. But probably, yeah, by the end of this week.
Maybe by the end of this week or by around next week. Yeah.
Right.
Okay, thank you.
Yes. Any more questions?
So next class is going to be what topic, sir?
Yes, so next class we will a little bit discuss about so we discussed about space-time translations. Next we will talk about what are the consequences of Lorentz transformations. And as you would have guessed, we will get boosts and rotations, those kind of things. So angular momentum and boosts we will get. With that, we will conclude classical field theory, and then we will move on to quantizing the complex scalar field. Okay. The complex scalar field that we, yes.
You touched on a little bit, yeah.
Touched on a little bit, yes. And there are many open-ended things that I have left, which I hope to come back to it, like explaining that the massive scalar field leads to a system of decoupled harmonic oscillators and these kind of things. So we will slowly see all those things. Now, there is let me look at some things. Yes, what does boost symmetry conserve? Yes, that's a very good question. We will see that what does it conserve first thing in the next class. I was actually hoping to finish all of this today, but I was a bit slow. But yeah, we will do this. Then what? Let me take couple more questions, and then we will end today's lecture. What particles do complex scalar fields describe? Yeah, so as Rakin has answered it nicely. So yeah, so if you want to study standard model, the Higgs sector, then yeah, that's a nice way to study it. If we add a perturbation to the action, will it break symmetry? Yes, if you add so at times you can add perturbations which respect symmetry. At times you can add, so imagine like you used to do in perturbation theory in quantum mechanics, you had an interaction term. So if you add that interaction term in such a nice way, for instance, for instance, note that we discussed this Z2 symmetry. So we said phi going to minus phi was the symmetry of the Lagrangian of this model, right? Where V phi was this. But however, if you choose to write a term like this, let's say you add a perturbation term like this, then this breaks the symmetry, right? This breaks this symmetry. So it depends on your choice. So for example, for Z2, if you want to write a Z2 invariant thing, you have to write as every even powers of the fields. Odd powers will break it. There's a correction that it should be half d mu a mu. Okay, so Ahmad says that probably I have written the exercise on the vector field Lagrangian with a mistake. So thanks for pointing out. I'll check it out. Yeah. Yes, there was another question which I deferred. So the question was, why didn't we take time as an operator? Yes, that's a very good question. So the way quantum field theory was, mm, yes, the way quantum field theory came up was to treat all the coordinates, uh, t and all the space coordinates as just coordinates. None of them are operators, and we are treating all of them in the same footing. Okay. Another way we could have done was, because in Schrodinger equation you have an operator which is like the derivative of the time, kind of a thing with respect to time. We could have also looked at the space coordinates as operators, but turns out that's a bit difficult, and so that's why we decided that we will demote even time to the status of a coordinate, not an operator, and we will do that. One benefit of this is that actually time is just a coordinate, like we know in special relativity. It's not a special thing, unlike we learned in classical physics or relativity. It's just like any other coordinate. The fact that we just, like you go left and right, you can't go past and future, is because you are inside this light cone, and things only happening inside this light cone can affect you. But if you are outside the light cone, like let's say if you are here, then there doesn't exist anything called time ordering. So time ordering doesn't exist. Past and future are blur, but there is something called space ordering. For instance, people here, like whatever that universe is, they will all agree that left is absolute left and right is absolute right. Okay. So, but we in nature we don't live in that part of the universe. So hence going past and future is forbidden, because we live in a time ordered universe. Otherwise, time is exactly like space. Okay. So that's why we demoted everything to coordinates. Maybe that was not a great way to explain your question, like answer your question, but okay. Yes. So I think I have exhausted all the questions in the chat.